everyone, my assessment is all about pneumatic controller or pneumatic control system. This is the air compressor, filter, regulator, lubricator that lubricates our system. It goes to the controller, and we have two solenoid. These are the double acting cylinder. This for our pneumatic controller. This is the electrical control circuit or control circuit of pneumatic system. This we have SB1, R1, SB2, and R2. SB1 means start, bottom, 1, and R1 means relay. And we have K1. K1 means solenoid. K2 means solenoid 2. And we have normally open and normally close contact.
Good afternoon, sir. Good afternoon, classmate. Today I will discuss about the hydraulic system. Although systems are designed to suit particular application, basic circuits and associated equipment can be identified as shown in the picture. In the figure, motor speed is controlled by adjusting valve A to control speed. The circuit could be of a windlass mechanism or of a deck crane mechanism. In case of circuit of windlass, the motor shaft will be doing the duty of heaving up the load of the anchor. 5 main categories of equipment to achieve this power transmission in hydraulic system are the hydraulic pump to convert mechanical into hydraulic energy, valves to allow this hydraulic energy to be controlled, hydraulic cylinders to convert the hydraulic energy into linear force and motion, or hydraulic motors to convert the hydraulic energy into continuous rotary motion. Ancillary equipment including filters, heat exchanger, tanks, pipes, etc. to complete practical circuits. And also in the picture, we have electrical circuit of electro-hydraulic control system, which is 24 volts. Our source is 24 volts, and we have little outlet, which is the ground. And we have here circuit 1 and circuit 2. In circuit 1, we have start button 1, and we have LS2 or limit switch 2, and we have solenoid K1. In circuit number 2, which is parallel in our circuit number 1, we have start button number 2 and LS1 and solenoid K2.
Good day again. I will show you a diagram and let's evaluate together how PID used as a controller. So I have here the diagram. Let's first label this one. This is the steam. This is the air supply. The control bulb. Control bulb. So, what is the function of our control bulb? So, the control bulb, it is used to regulate the pressure or the flow rate of the liquid. Then next, the oil fuel heater. Oil fuel heater, and this is of course the oil fuel. This one, it is the controller. This line, the condensate. It's the condensate. And this line, let's trace this line. This is the positive displacement sampling pump. And of course, this, what did you call this one? This is the capillary. Capillary. What's the use of the capillary? The capillary, it will help to maintain the needed pressure difference for proper system operation. It can be also used as throttling device because of the small hole into the pipe. That's why it can be used as throttling device. And this one, this is the DP transmitter. So what is DP? DP stands for differential pressure transmitter. So what's the function of differential pressure transmitter? It's used to measure the flow rate of fluid throughout a pipe. So after the differential pressure transmitters, as you can see, it will travel to capillary tube. Then this one, our last device, it is the recorder. So that's it. We already label the parts, and this diagram is a sample of fuel. This is the fuel pump at constant rate through a fine capillary tube. So this is the constant rate through a fine capillary tube. A differential pressure transmitter provides analog viscosity to a pneumatic controller. This is the air controller, which regulate the supply of fuel heating steam through a control bulb. So that's it. That's our entire system. It's just show you the pump, the fuel pump at a constant rate through a fine capillary tube.
My assessment is about how a PID is used as a controller using the institution that replicate a particular shipboard system or machinery. Automatic controllers are used on board ships for the adjustment of one or more parameters in a system. Function of the controller is to maintain the parameter as per desired value. The parameter could be jacket water temperature for engine jacket water cooling system, lubricating oil temperature for engine lube oil system, fuel oil pressure for boiler fuel oil system, etc. PID controls are commonly used for these applications. On-off or two-step action. This is the simplest form of control. Here only two control positions are allowed, on or off. In the case of the valve, it opens or closes by the signal from the controller. Examples for such control system are water level control for boiler cascade tank, air compressor cut-in, cut-off control, temperature control for fuel oil storage tanks. Consider a water tank with an outlet valve, a water supply valve, control lever on a pivot control strings, and float as shown in the figure. One end of the control lever is connected to the float while other end to the water supply. The system is designed in such a way that when float goes down, supply valve is open, more thereby increasing water supply to the tank. Similarly, an elevation of the float results in closure of the supply valve. At this point, quantity of water supplied and flown out of the tank is same or the system is in equilibrium. Here, in addition to the feedback bellows, we have integral action bellows also. Consider the integral action valve is open. Now as the flapper moves closer to the nozzle because of a deviation, output air pressure increases. The same air pressure acts on feedback bellows to move the flapper away from nozzle to an equilibrium position. Now there is an offset again. The same control air pressure acting on the integral bellows move to the flapper towards the nozzle to increase control air pressure. Hence, a new equilibrium is attained with no offset. Note that all the action take place simultaneously. Here, a derivative action valve is introduced as shown in the figure. Closing this valve any amount will introduce derivative action in the system. Consider the derivative action valve is closed 70% when flapper moves towards nozzle because of a deviation, controller output pressure increases. The same pressure acts on the feedback bellows through the derivative action valve.